Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Today we are going to look at some basic functions under the topic of the broader topic of or concept of calculus. And this is going to be a foundational, of course, kind of a discussion whereby we're going to look at elementary real functions which are going to appear in one way or another in various discussions on the topic of calculus. Now, in this case, I've mentioned various types of functions and what basically the concept of a function relations entail. So in this case, I'm going to just give a few or a list of functions which you may come across in one way or another. And of course, I'm going to explain in a short or a summary form some of the characteristics of these functions that we may come across. So the first one is the zero function. The zero function. And this specific zero function, we're going to look at its specific domain and the range which we are given in various concepts for that, especially when we were discussing about the concept of trigonometric functions. So in this specific case, for a zero function is going to be also regarded as a zero polynomial. In some cases, we're going to see also how we can be able to graphically represent these kind of functions. So in this case, for a zero function, its domain is going to consist of a set of real numbers, which we are going to give in terms of r given as such. So that, of course, apart from that, we're going to see that the image of this specific zero functions is going to be a zero. And of course, we can be able to graphically represent this kind of a function as a x-axis, whereby if we use two Cartesian coordinate system for x and y, then therefore we are going to give this specific zero function as the x-axis given as such. So this x-axis can be described in terms of the function of y is equivalent to 0, since we do not have an of course a set of change in the y given as such. So therefore this is going to be described as the x-axis, and this is one of the way in which we can be able to describe this particular set of a function that we refer to as a zero function. So therefore, in summary form, I've said that a zero function is also going to be referred to as a zero polynomial, and its domain consists of real numbers given as r, and of course the image of these zero functions is going to be expressed in terms of 0, and of course we are going to give it in terms of a graph as the graph of y is equivalent to 0. The next we are going to look at the second part of it, which is basically a set of functions that we're going to come, elementary real functions that we're going to come across in calculus. So we're going to look at this set of functions that we refer to as polynomials. Now I've talked about various discussion about the set of or a set of discussions. I've talked about what basically polynomials entail, and we talked about the concept of a monomial, binomial, and polynomial in that specific order, and the various terms that of course are contained in this specific monomial, binomial, and polynomials in that specific order. So in this case, we are going to see that in contrast with the first one that we discussed of a zero function, polynomial is going to be given as a real non-zero polynomial function. And of course, I've talked about the zero function. So this is going to be given as a real non-zero. So it's going to be a real non-zero function given as. So we are going to expect its domain to consist of a slightly different set of course, numbers as we are given in this specific case for the zero functions. And of course, we're going to define this specific function in some kind of set which is going to consist of coefficients which I'm going to give on the board. So this polynomial can be defined as a function of x given as a, of course, this is a subscript n, and of course this is a coefficient, and therefore a term is going to be given as m x raised to power n. And then we're going to have this specific coefficient and the term of n decreasing in a particular order, whereby we're going to have this particular coefficient moving in this specific set. So we're going to have these particular terms extend to a point of having this ax raised to power 1, and then the last term is going to consist of this particular coefficient that we're going to give us a. So this in this specific expression for a polynomial, the set of these particular numbers we're giving as n are going to be given as numbers greater than 0. And of course, for the coefficients which I've given in terms of a, of course, ranging from a0, a1 to a to power n, now that I've given this range of n, are going to be a set of real numbers. So this is going to be a set of real numbers whereby a raised to power n is not equivalent to 0. So that's one of the conditions that we're going to see being expressed in this set of what we refer to as a polynomial or a non-real or a non-zero polynomial function given as such. So in some cases, we're going to come across the concept of a decrease, whereby the function f is going to be, or is said to be of a degree, a particular degree n, which is going to be given a term of a real polynomial of a degree n. And therefore, we can be able to give this specific function that we have said for this particular set of n. So in case if it's this particular number is 2, which is a set of real numbers, as we said, then we're going to see that this is going to be a second degree, where n is 1, the first degree, and then of course as we go on, we're going to describe the third degree in that specific order. So that's how we can be able to describe this particular function. And this polynomial, which is a function, is going to consist of a domain of a range of real numbers, as I said. And of course, the graph of this particular function can be given in terms of y is equivalent to a range of numbers. So in this case, I'm going to consider a few examples of this specific set of the number n. And of course, we have said that the number n is going to depict the degree of that specific polynomial. So I'm going to look at a set of 4. So in case this in this particular function, in case n is equivalent to 0, this one can be expressed in terms of the function fx is equivalent to a, I know it's given as such. And of course, we can be able to note this one from checking on these specific coefficients for the value of n, whereby we are seeing that if n is equivalent to 0, this n is equivalent to 1, and therefore n equivalent to 0 is going to be given as this first coefficient. No, so these terms of polynomials are going to be given in the term of a constant function, with the value of a being given as such. So the graphs of these specific functions are going to be a set of lines, of course, which are going to be given parallel to the x-axis. So if we try to represent this specific function in terms of a graph, and this is the value of y is equivalent to an, which is of course a constant. So if the value of a is equivalent to 2, then therefore we have said that these are going to be lines representing this specific, of course, set of functions which are parallel to the x-axis given as such. So this is just a function which is a constant given as such, and the value of n is equivalent to 0, as I've said. So the second set of functions are functions which are going to be described in this specific form, whereby we're going to have n equivalent to 1 given as such. And as we can see from this specific description, then therefore the value of y is going to be described, or the function of x is going to be described as a1 x1 plus a0, which basically states, we can be able to observe that it consists of a coefficient, the value of x equivalent to 1, and then this specific function. So it's going to consist of these two sets of the last function given as such. And of course, we can be able to give it in a general format as I've given as such, whereby for all values of x, as I said, they're going to be a set of real numbers, as I've already mentioned. Then this particular kind of functions are going to be given a term, which is going to be a linear function. So the first one, I said that they're going to be constant functions which are going to represent lines parallel to the x-axis. But for this kind of a function where the value of n is equivalent to 1, they're going to be given a general representation as such. And this is going to consist of a value of x where for all the values of x are going to be a set of real numbers. Then therefore we're going to refer these ones to be linear functions. Now we have already discussed about the concept of the function of a straight line, which is y is equivalent to mx plus c. So if we said this c is a particular constant, we can be able to give analogous function of this specific set. M is going to represent a coefficient, A1, which is basically from description is the gradient of that specific line, and X is going to consist of that specific term raised to the first power given as such. So these general types of course, polynomials are going to be given the term a linear function given as such. So we're going to look at also the second set of a function whereby n is equivalent to 2 in that specific set. So this particular function for the value of n is equivalent to 2 is going to be given a general expression for fx is equivalent to ax squared. So this term n is equivalent to 2 plus a1 x1 given as such, and then we're going to have plus a0 given. So it's going to consist of 3 terms, whereby we say that for all values of x, x is going to be given as a set of real numbers, as I had mentioned before. So this set of functions which are going to appear in this specific format are going to be given a term that we refer to as a quadratic function. So this is going to consist of a set of quadratic functions, and as well we are going to find the graphs of these specific quadratic functions being given in terms of parabola. So the graphs of the first graphs we said are constant. The second graphs, as we said, for n is equivalent to 1 are going to be linear functions, and then for this particular graph for n is equals to are going to be quadratic functions, which are going to be basically parabolas, which can be expressed in a general term as y is equivalent to a squared x squared plus ax plus, of course, the last term, which is a not given as such. So basically, as you can see, as we are developing along, we are coming with various types of course, functions, which we are giving specific terms which you have come across in various discussions. So this basically are some of the functions we're going to encounter in our various discussions on the concept of calculus. And lastly, like I said, of course, we're just going to look at a few. We're not going to look at a higher degree functions, and this specific case, then therefore I'm going to look at the last one, whereby the value of n, or for a general term, the value of n is equivalent to 4, and other ranges of degrees above this specific representation. So therefore, for this set of polynomials, they are going to be given specific terms, which are going to be referred to as cubic, quantic, etc. So we're going to discuss this one perhaps in a different video, but in summary form that I wanted, of course, the main concept that I wanted us to find from this, or to understand from this specific discussion, is that there are various ranges of elementary functions that we're going to come across in calculus. And of course, this discussion was to shed light on some of these specific functions and how we can be able to graphically describe them and give them in terms of algebraic form. So the first one I said is a zero function, whose domain was a real number, and then the image was 0, and the graph basically was the graph of the x-axis. That is, of course, is going to consist of the graph of y is equivalent to 0. The second type of functions that I mentioned was polynomials, and this, of course, I've created emphasis since most of the functions, the non-zero functions, are going to lie in this specific case. And I've given a general representation for a polynomial using these particular functions. Now, for the different range of the values of n, which are described, of course, which consist of numbers equivalent to or greater than 0, this formed a set of real numbers, which, of course, we said that this particular coefficient we have given for the value of n, of course, are going to be given in terms of numbers greater than or numbers which are not equivalent to 0. Therefore, we can be able to describe the general case for a polynomial using this particular set of elements that have or terms that I've given above. So the first case for the value of n is equivalent to 0, we had said consists of constant functions, which are basically functions which are going to be expressed as parallel to the x-axis. And then next we said that for the value of n is equivalent to 1, we have a set of functions which we say were linear. And in that specific order, then therefore we said that this n is equivalent to 1, n is equivalent to 2, we said this a value of functions consisting of quadratic functions. And then lastly we said that n is equivalent to 3 and other higher values, these are going to be given in terms of cubic, quartic, and that specific order. So catch us in our next videos. We're going to look at the second bit of these elementary functions of calculus, and that's going to form our last bit and the closing of video for basic discussions on the concept of functions in elementary level for calculus. So that is it for us. Bye guys, catch us in our next video.